Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. So far, we've learned how waves respond when they arrive perpendicular to a fluid interface. In this video, we'll gain new intuition regarding the reflection and transmission of acoustic waves when they arrive at an oblique angle between one fluid and the next.
So let's get started. In many environments, sounds strike interfaces at a wide variety of angles. These are many angles of incidence. This problem is slightly different than the wave behavior that we've seen before, when waves are perpendicular to the fluid interface. So we need to apply our theory once more. The same boundary conditions hold, but it's a slightly different flavor to what we've just learned. The frequencies still need to be the same as we had before, but our pressures exist in both x and in y. The x is 0 plane is shown here, and the x-axis goes to the right. We actually define y positive as being down, and in this way our acoustic pressure that's incident, complex acoustic pressure, has vector components in x and y that we'll write in the complex exponential. The amplitude is capital P sub I, and then we have e to the j omega t minus k1 x cosine theta I minus k1 y sine theta I. The reflected acoustic pressure down below has amplitude complex P sub r, e to the j omega t plus k1 x cosine theta r minus k1 y sine theta r. We note that both the incident and reflected acoustic waves have a minus y in the complex exponential since they move in the same y direction. On the other hand, they have flipped signs for the x in the complex exponential since one moves to the right and one moves to the left. Our transmitted acoustic pressure, P sub t, has amplitude capital complex P sub t, e to the j of omega t minus k2 x cosine of theta t, which will make as complex, and we'll learn more about that soon, minus k2 y sine complex theta t. Now our first boundary condition is that pressure must be continuous at the interface, and the interface is the plane x0. Our equation for that continuity is shown here. Each complex exponential has a quantity in terms of the location y. But in fact, this needs to be true for any location in y, since our incident wave could arrive at any location along the y-axis. So this means that all of the exponents need to be equal. We find two things when we apply this continuity. First, it means that sine theta I must be equal to sine theta R. In other words, the reflected angle needs to be equal to the incident angle. We intuitively already know this for light. The second equality, when we equate the complex exponential on the left side to the right side, is something called Snell's law. And this is what we find to be sine theta I divided by C1 must be equal to sine of complex theta t divided by C2. Considering our continuity more closely, we find the pressure reflection coefficient using the continuity of normal specific acoustic impedance. Our complex pressure reflection coefficient is R2 divided by R1 minus cosine of complex theta sub t divided by cosine theta I, all divided by R divided by 2, R2 divided by R1 plus cosine complex theta t divided by cosine theta I. Now, By rearranging Snell's law and considering this complex pressure reflection coefficient, there are three possible outcomes that can occur. The Snell's law states that the cosine of the complex transmitted angle is equal to the square root of 1 minus c2 on c1 squared multiplied by sine squared of the incident angle theta I. This square root could go imaginary based on two things, theta I and the ratio c2 on c1. The first outcome is simple. c1 is greater than c2. And in this case, theta sub t, the transmitted angle, is always real, and it's always less than theta I. A good example when c1 is greater than c2 is the water-to-air interface. Now in this case, the video is edited in magnitude since the amplitude in air is still very small, just as we saw for normal or perpendicular waves at interfaces. What we find is that the water wave reflects out of phase, likewise what we saw before for normal incidence. And the transmitted air wave responds at a transmission angle less than the incident angle. We see the transmitted angle approximately here, and the incident and reflected angles approximately here. The second outcome is that C2 is now greater than C1. This is similar to our air-to-water interface example. But theta I is less than a quantity, theta sub c, and we'll describe theta sub c momentarily. This simulation shows that type of case, an air-to-water interface when theta I is less than theta c. We see our transmitted angle is greater than our incident and reflected angles. The wave is bent in water compared to the incident angle in air. We momentarily skipped over it, but theta sub c is the critical angle, and sine of the critical angle is equal to c1 on c2. It's important to recognize that when our incident angle is equal to our critical angle, there's neither transmitted pressure nor transmitted power. And we see this in this simulation of an air-to-water interface when the angle of air arrives at the critical angle. Something like a wave propagates in water, but not really if you pay attention to it. Instead, what we're seeing is that the wave in water is almost hanging on to the interface, and it decays as you look further into the field of the water. The reflected pressure, on the other hand, is nearly the same in amplitude as the incident. What happens in the third case? When C2 is greater than C1, for instance, air to water, and the incident angle is greater than the critical angle. By the equation that we saw earlier from Snell's law, the cosine of theta t is imaginary. And when theta I is greater than theta c, this means that the transmitted pressure decays exponentially in x. And we have a new transmitted pressure formulation that we see here, with the decay constant gamma that's computed using Snell's law. This is called an evanescent wave. It refers to a wave that may propagate but decays exponentially in its direction of propagation. And we see that here in this simulation. The incident angle is greater than critical, and there is not a transmitted wave into the water. The wave literally hangs on the surface of the interface. This application of critical angle is applied in optics, and it's actually referred to as total internal reflection when C2 is greater than C1 and the incident angle is greater than the critical angle. It's used in the development of diamonds. Specifically, the diamond cut is based on how well it can perfectly reflect light out and up. So for instance, a diamond cut that's too steep does not apply the total internal reflection principle. In other words, the incident angle is greater than critical. In this case, the light passes mostly down beyond the diamond. The diamond would look clear. In the case of a too shallow cut, the light is unequally diffused back out. But for a perfect cut, the light reflects out and up back where you're looking, so that the ring that you're looking at sparkles in every direction that you look at it. This principle is likewise just as applicable to spherical waves as it is for plane waves. The theory behind both oblique and normal acoustic pressure reflection and transmission at the interfaces is directly applicable. So for a spherical source, if the waves are perfectly normal to the water, from air to water, they transmit, and some reflect, of course. As the angle of incidence increases, we have bending of the wave, in other words, refraction in water and reflection in air. And as we approach the critical angle, less and less of the wave transmits into the water until we are above critical and all of the wave reflects. Naturally, of course, regardless of the direction of incidence, this is true up until the critical angle. Acoustic reciprocity also holds for all of these cases except angles of incidence beyond critical, because there's spatial dampening, which is a non-conservative phenomenon that's not applicable for reciprocity. So in this simulation, we see a spherical source above water, air to water. And what we find is that the wave that propagates in water does not propagate for all angles of incidence. For instance, we see at approximately this location and mirrored on the other side, the wave does not pass. It's dampened due to the evanescent phenomena for those steeper angles of incidence. So when we take this into account, for nominal spherical waves in the environment, all the directions of waves incident upon this layer, they are perfectly spherical, but this theory applies just as well. So let's summarize what we've learned. We've learned that acoustic waves that are incident at oblique angles to interfaces reflect and transmit according to two things: the relative differences of phase speeds and the exacting angles of incidence with respect to the critical angle. Refraction occurs precisely according to Snell's law, and beyond the critical angle of incidence, waves do not transmit between the fluid layers, and total reflection occurs back into the incident fluid. And this theory is quite easy to develop with plane waves, but applies to all spherical waves day to day.
That's it for this video. In the next video, we'll see how this principle of reflection and transmission near fluid interfaces applies when sound sources are placed near an interface.